I have, I guess, 6 or 7 prepared here that we'll go through in just a second. All right, as people continue to come in, just add your questions to the chat. I'm going to start a quick. Well, I'll do the poll later on. We'll start with a molarity question that we covered in chapter 13, I think. So we'll start there. Again, type whatever subjects you want to see covered in the chat, or exact practice problems from the practice exam, or any particular topic, and we'll go from there. And let me know if you want different music or anything like that, or no music. Okay, so here's the first one that we're going to solve. Obviously, molarity is something that you're going to need to know how to calculate on the exam. So this one in particular is a little challenging in terms of how it's set up. So it asks, what is the volume in milliliters of 6 molar nitric acid that contains a certain amount of grams of nitric acid? So as soon as we see this molarity here, it's going to be one of 2 types of problems that we've covered. Okay, either it's going to be a dilution type problem, or it's just going to be a straight molarity calculation. And nowhere in this problem is it mentioning dilution or a change in volume or a change in concentration. So it's not a dilution problem, it's just going to be a straight molarity problem. Okay, so I'm just going to write down the information that's given in the problem. This is how I would expect you to attack it. Writing the formula for molarity, which is always moles of a certain compound. Here it's HNO3. Yep, dilution is weakening anomaly, so you're just adding more solvent. You're not changing the amount of moles of solute. And molarity is always moles of solute over liters of solution. So in a dilution, you're adding solvent but no solute, so the whole concentration gets weaker. Oh, awesome. Oh, that's so cool. Anomaly uses streams to help homeschool 10-year-old and middle school science. That's really, really cool. That warms my heart. Here's the formula for molarity. Moles over liters. So we're asked for a volume. I know that means we're ultimately going to be solving for the denominator here, liters of solution. The numerator is moles, so we must have enough information to calculate that, and here we're given the grams of nitric acid. So I know somehow I can use this grams of nitric acid to get to moles of nitric acid, and by now in the course we've been doing this a lot, converting grams to moles. Okay, that's always done with the molar mass. Okay, so we just need the 1 unit factor here. The molar mass of HNO3, you can add up on your own. It's 48 from the oxygens, plus 14.01 from the nitrogen, plus 1.01. So that should give me 63.01, 48, 58, 62, somewhere around there, 63.01 grams per 1 mole. Or I suppose 63.02, since it looks like it's going to divide out evenly. So this should give us about 0.100 moles of HNO3. That now goes in the numerator. And so it's 6.00 molarity equals 0.100 moles of HNO3. Nagin Sali, thank you for the follow. And George, 1435, followed before I came on. Thank you, George. Okay, so now our molarity calculation has been limited now to this. And now we just solve for the question mark. It's just an algebraic rearrangement. Basically, you're changing the position of 6 and the question mark. So x, or question mark here, equals 0.100 moles over 6. Molarity, where molarity is moles per liters. So you can keep track of units and see moles are going to drop out and leave us with liters. we should get 0.0167 liters. Okay, of course, the question asked me for milliliters, so now I have to take this, and I've run out of room here, but I have to take this liters that I've gotten, I squeeze it in up here in the top right, and convert this to milliliters. Okay, in 1 liter there's 1,000 milliliters, so this number, we basically move this decimal point 3 to the right, and our final answer then should be 16.7 milliliters. Okay, any questions on that? I didn't prepare a ton of practice problems, like I said, 6 or 7. So if you have additional ones you want to see covered from the practice final exam, again, just paste those in the chat. Okay, so that's pretty much it for molarity. Identify it as a molarity problem because it's, giving you a molarity concentration. See if it's a dilution problem. If it is, it's M1V1 equals M2V2. Okay, but this is not a dilution problem, it's just the molarity formula. And so we started there and sort of laid the roadmap for how we were going to work through this problem. All right, we'll go on to the next one. And you should be attempting these, by yourself, as I'm going through them as well, right? This is the first time you're seeing it, so it's just like on the exam. It's the first time you're going to see a certain question. So try to identify what kind of question it is and start attacking it right away. Are you going to do any dilution problems? I can. I don't think I have one prepared here, but yeah, I'll add in a dilution problem for sure. Make a note of it. And remind me later if I don't. I want to get through these 6 or so that I prepared because some of these are going to be word for word on the final. Right, a couple of these. All right, so you should be attacking this one. What mass of silver is produced from 6.35 grams of copper? Yeah, no problem, Janine. Yeah, the last one, it should have been in milliliters, and that was sort of the last step here. So I'd solved it for liters, but I was asked for it in milliliters in the question. And so quite sloppily up here on the right, I did that last conversion. So liters to milliliters is 1,000 times bigger. There's 1,000 of those small milliliter units in one large liter unit. Okay, so that was this conversion that I sort of hastily put up here. George, sure, I'll do an isotope question, or that exact one. Make a note of that. Dilution and isotopes, we can surely do those. So you should be working through this 6.35 grams of copper. All right, this is a pretty short question. I'm always going to write what I'm given on the left. And ultimately what I want to get to on the right, mass of silver. Mass is grams, so I'll write G of Ag. You're welcome, Janine. So what mass of silver is produced from 6.35 grams of copper? Okay, so this is a stoichiometry, a mass-to-mass stoichiometry problem. Okay, so we know it's going to be, just like one of the calculations we do as part of our limiting reactant ones. Okay, it's just a single stoichiometry calculation that is always going to have 3 unit factors, right? A molar mass, a molar ratio, then a molar mass. Okay, but the first thing we do before we start filling this in here is balance the chemical equation. That's always our first step. Okay, is write the equation if we're not given it, and then balance said equation. So here we have 1 copper on each side, 1 silver on each side, but we have 2 of these NO3 units on the right. So we better put a 2 out here on the left in front of silver nitrate. And now that we've done that, nitrate is balanced, but that's created an imbalance in silver. And so a 2 in front of silver will fix that. Okay, so 6.35 grams of copper. We need the molar mass of copper. Why do I know that? Because as soon as we're given grams of copper, we're going to want to eliminate that unit. So that has to be the first unit in the denominator here. Okay, and a unit factor that I know is grams per mole of copper. right? That is the molar mass. And so I consult the periodic table, 63.55, grams per 1 mole of copper. Okay, so now I have moles of copper. I need to get rid of that unit, so that better be in the denominator of my next unit factor. This middle unit factor is always going to be a molar ratio. This is what gets me from copper to silver. So it's moles of copper compared to moles of silver. And this, I consult silver and copper, or whatever compound you're trying to go from and to, in the balanced chemical equation. Mason, thanks for the follow. Appreciate you. Welcome. There's 1 is the implied coefficient out here in front of copper. There's 1 mole of copper for every 2 moles of silver, right? I balance the equation to be able to relate this recipe of moles of silver to copper. It's a 2-to-1 ratio. There's two silvers made for every 1 copper and 2 silver nitrates. Okay, so now I'm in moles of silver. So my last unit factor here better get rid of that unit of moles of silver, and it better go to what unit I'm trying to calculate. Okay, so that's another molar mass. So these are always going to be molar mass, molar ratio, molar mass type problems. And for silver, the periodic table tells me it's 107.87 grams per 1 mole. And I get something like 21.557 grams of silver. Okay, if you're not getting that, make sure you're familiar with your calculator and using parentheses if you have to, just taking your time to multiply across everything on top and divide by everything on the bottom. I always have to worry about sig figs. The only digit I'm given in this problem is 6.35 grams, which is 3 sig figs. Everything's multiplication here, so I'm going to be limited to that same 3 sig figs. So this 21.557 should become 21.6 grams. And so that should be my final answer here. Okay, any questions on that one? I'll wait a minute or so for questions, and I'll maybe go to the next question and let you try to work on it ahead of time if you don't have any questions. If you have questions on this one, go ahead and voice them, and I'll go back and cover that. Otherwise, try to proceed and work on this next question. Thanks, Mason. Glad you like it. This is the final exam review for my introduction to chemistry class. Usually I'll stream twice a week. One's office hours for the class. The other one is for the class as well if they want to come and ask questions, but it's also more for a general audience. So usually on Tuesdays this semester I've been doing office hours, and Thursdays I've been doing sort of a general audience stream about the NASA mission to Mars and landing on Mars, or the gene-edited twin girls that just got born in China, or whatever sort of the scientific news is. I usually cover that on Thursday. All right, so let's proceed. Hopefully you've been working on this electron configuration of fluorine. And I've added these captions here at the bottom because to make it more accessible, but also because some people are at work or don't have headphones or might not be able to listen while they watch. So they're not perfect, and sometimes they're quite humorous, but they do a decent job, I think, of speech to text conversion. Beast Wheatley, great name. This question is essentially just asking for the number of valent, no, not number of valence electrons. The electron configuration will usually have a notation stating the energy level, and this is probably a good chance to review some other topics. So this is the sort of electron notation that tells you the energy level, that's the first number there, the sublevel, whether it's S, P, D, or F, and then the number of valence electrons. So it's energy level is this first number, sublevel, and energy level is usually 1, 2, 3. Sublevel is S, P, D, F, and this is the number of electrons in that sublevel. Okay, and so the electron configuration for an element specifies where all the electrons are, right, throughout the whole atom, not just the valence electrons, beast. Okay, so for fluorine, we consult the periodic table. It has 9 valence electrons, or 9 total electrons. And now you got me concentrating on the valence, beast. That's all right. So fluorine, 9 total electrons. So we know that these numbers, once we write out the whole configuration, should add up to 9. Okay, and you can either memorize the order of the sublevels and energy levels, or you can sort of read through the periodic table once you're familiar with the S block is the first 2 columns on the left, right? So the periodic table, if a poor artist was to draw the periodic table, it would look something like this. Okay, these over here is the S block elements. These over here are the P block elements. And these in here are the D block elements. Okay, and the rows are numbered 1, 2, 3, 4, etc. Although D is a little tricky here, this first one here is technically 3D, and then the one underneath that is 4D. So just reading through the periodic table, we go through the 1 and S block first, so 1s. Then, technically, I guess this should be chopped off here. There's nothing that lives here. Just hydrogen right here, and helium over here. And both of those are the 1s sublevel atoms. Okay, so there's 2 atoms in that 1s level. Then we come down here to row 2. We go through the S block first before we get to the 2p block. Okay, and fluorine lives almost at the end here of the 2p block. Okay, so we pass through 2 elements in the 2s block, and then fluorine is the 5th element in the p block. Okay, so there's 2 plus 2 is 4, plus 5 is 9. So this is the whole electron configuration for fluorine. 1s2, 2s2, 2p5. Notice if I asked F minus, right, that would hop 1 electron to the right and become 2p6. If it was F plus, it would hop 1 to the left and become 2p4. If I wanted the abbreviated configuration, I express the core electrons with the noble gas, followed by just the valence electrons. Okay, so that's all the types of questions you might see for electron configuration. Yeah, you got it, Beast. Any other questions? Otherwise, proceed and try to tackle this problem. Can you guys hear the music at all? That's probably okay. Yeah, I turned it down some. It was just sort of background Christmas music. I don't know if you're in favor of that or not. Okay, I started a poll. Vote in chat. 1 for you don't want music. 2, yes, but a little quieter. 3 for yes, it's good where it's at. Or 4 for yes, we want music, but louder. Hey, Anabeta, hello. We're doing some review for my Introduction to Chemistry class. The final is on Monday or Wednesday, depending what section they're in. So we're just covering some topics and practice problems and whatever they want to discuss. So shout out for Ina Beta. I was watching him the other night. He was discussing anatomy, various terminology. He was discussing on another stream sort of basics of neurons and how they work. He also plays some games, so if you're into biology, neuroscience, anything like that, go check him out. He's a member of the Knowledge Fellowship, which is an expanding number of educational streamers on Twitch. So you can check a bunch of different people out that talk about geology or chemistry or physics, whatever subject you like. Yeah, no problem. Thanks for hanging out. We'll finish the poll there. Yes, in a landslide. I knew I liked you people. We'll leave it where it's at. Okay, we'll start another poll for the answer to this current problem before I solve it. Wait for the poll, Karen. It's all good. What are the final times? That's a great question. It's in the syllabus, of course. The class that meets 10 to 10:50 is Wednesday at 9 a.m. The class that meets 11 to 11:50 is Monday at 11 a.m. Best to go check the syllabus or UNF's breakdown, all that, double check, but you got it. Oh, there's a lot of diversity here between bent and tetrahedral. I'll give it another minute or so as I walk through the other. Problems here. So what? Add electrons. So various steps. Move some non-bonding ones if necessary. All right, maybe we'll stop the poll there. Most people vote bent, a couple tetrahedral. and a whole bunch of people that don't want to vote, abstain, or are not confident enough to vote. Remember, bonus points are on the line here, people, for correct answers. Okay? Bonus points don't count towards your final grade. Alright, so molecular shape of H2S, we have to first draw the Lewis structure. Unless you have these memorized or something, you don't have to do all this, but generally, for these types of problems, we're going to draw the Lewis structure and then use our table of bonding versus non-bonding to pick out the molecular shape. So valence electrons here, 6 from sulfur, 1 from each hydrogen, that's a total of 8. What is the central atom here? It's usually going to be the first atom written, but in this case, hydrogen is never going to be the central atom, so it's got to be sulfur. I guess the second part of step 2 is immediately draw an octet around that central atom. 2 electrons on each side, north, south, east, and west, to give us 8 valence electrons. I'll add the other atoms now. Here are the hydrogens. And you can put it on whatever 2 sides you want. Maybe I'll put it here and here. Okay, add any remaining electrons, but we've already used up our 8, right? So we actually have 0 valence electrons left. Okay, so don't be tempted to draw more electrons out here on each hydrogen. For one thing, you don't have any more to draw electrons. That would be 10 electrons, 10 dots, and we don't have that. Okay. Secondly, everything wants 8 electrons around it except hydrogen, which only needs 2, and it has access to these 2 right in here, sharing with sulfur. Okay, so we don't need to worry about moving any other non-bonding electrons to reach octets because everything is satisfied here. Every hydrogen has 2 electrons, that's its quote-unquote octet. Sulfur has 8, that's its octet. Okay. We're going to replace the bonding electrons with lines, and bonding electrons are between 2 atoms. So these pairs that are between hydrogen and sulfur, we replace with a line. Okay, so this is now the Lewis structure for H2S. Okay, it looks a lot and is identical to one we did in class, and a more familiar example perhaps for water, H2O. Because oxygen and sulfur have the same number of valence electrons, everything else is the same. Okay, so that's our Lewis structure. We can now pick the molecular shapes based on bonding and non-bonding electrons around the central atom. There's 2 pairs of bonding, there's 2 pairs of non-bonding electrons. Okay, and for this class, I give you access to the table that sort of explains what all these different geometries are. It's that second table down there. You probably can't read it. It's not going to focus, but you have access to that table, or you can look online right now. Don't, and the geometry that corresponds to bonding and non-bonding here of 2 and 2 is bent. So the correct answer here, most of us selected it right in the vote, was bent. Yeah, helium would only have 2 valence electrons also. Okay, any questions on that one? Right, not also, I guess, but it wants, its octet would be 2 electrons, and it has 2 valence electrons. Alright, so if you have any questions on this one, let me know. Otherwise, I will move on to the next one and put it up for you guys to work on, and maybe I'll start a poll. Would bent be synonymous with angular? Correct, Beast. It doesn't require an octet, because octet means 8. And a lot of things don't, actually, but at this level, we assume they all want to have an octet, except hydrogen and helium, which is just 2. Angular? I've never actually heard of shapes being angular, at least in Lewis dot structures and molecular geometries in a beta. But, yeah, I mean, it looks like this, where the hydrogens actually move closer together because those free electrons or non-bonding electrons take up a bit more space. They're not confined to a bond, so they actually take up a large amount of sort of area and push the 2 hydrogens together. So that's what it would look like. Cool. Number of valence electrons, always the group number of the atom. Sage, in terms of this course and what you'll be tested on, yes, because we only count S and P electrons as valence electrons at this stage, because d electrons are cray-cray. So if you look at the group number, at least the Roman numeral designation, right, there's numbers like 1 through 18, but the Roman numerals will usually specify the valence. So yeah, that's a quick way. Look above the periodic table column, what's the Roman numeral? If it's sodium, the Roman numeral's 1 valence. If it's oxygen, the Roman numeral 6 valence. So yeah, that is a shortcut, Sage. And this is my periodic table mug. It might not focus again, but there are Roman numerals above each column. My brother got me that for Christmas last year, so it seemed appropriate, as we can now officially start the holiday season. We're in December. So I'll put up a poll question here as you work through this one. Hey, Mids. Welcome. We're just doing some practice problems for my Introductory to Chemistry final exam on Monday or Wednesday. So a lot of my students are working through these problems, but it can be a good refresher for sort of fundamental chemistry, things like dimensional analysis or molecular shapes, like we worked on in the previous one, electron configurations, stoichiometry, limiting reactant, molarity, things like that. So we're sort of discussing all those concepts as we go and reviewing for our final. I'm doing great today. It is officially allowed to celebrate the holiday season in my house and in my office at least, so I'm spectacular. It's my favorite time of year. I got the Christmas music going. I've decorated my office, as you can see over my shoulder. I have lights around my window set to a timer. My chemistry is in the window. Lord Kelvin is the second is swimming around, liking the music as well. So things are great. How are you doing, Midnicorn? Y'all should go follow her. She's an experimental physicist in the UK. Streams a lot about quantum mechanics and really cool video games like Shift Quantum, which is a video game that sort of embraces and teaches the quantum weirdness concepts. Okay, and she's streaming later today, I think in another hour or so. What are you streaming about today, Midnicorn? Another member of the Knowledge Fellowship. Beast, that is a great idea. I froze a pumpkin on Halloween and shattered it. Frozen liquid nitrogen shattered it. Douglas fir, yeah, I think that's the next step. That's actually a really good idea. I think, though, class is going to be pretty anxious for the exam, that a demonstration where we blow up a tree is probably not the best idea. But I like where your head's at. I'll just do it for fun. Minicorn's doing a programming type game today, or Portal Bridge Builder, and learning more about bridges. Oh, nice, Beast. Okay, cool. First, Bradacula, in a beta, who is still maybe here, hanging out, is also a member of the Knowledge Fellowship. So if you just click on the link, you can read about the Google document all the different types of streamers. Alright, so let's close the poll. Hopefully you've had enough time to work through this. Try to remember your metric conversions. Yeah, you got it, Brad. Looks like an even split between 1 and 4, and also some votes for 3. Intriguing. Remember, bonus points on the line. You gotta vote to get those bonus points, which definitely do not count towards your grade in any way. They're just my internal catalog. And at some point I will start recording those and giving out units for you to redeem in some way. Yep. Kai Mama, or Chamama, 1993. Everything in the practice problem packet will be given to you on the exam. So the list of solvents, the list of molecular geometry, periodic table, obviously, pressure conversions, solubility rules, temperature conversions, activity series. So just that'll all be included. All right, so kilometers to capital M is mega, little m here is meters, little k is kilo, not to be confused with little m, which would be millimeters, okay, or mu m, which would be micrometers. All those metric conversions we have to have memorized for the final. Okay, although I do, it's holiday season, I'm in a giving mood, you can bring a 3x5 inch index card with whatever you want on it. Those metric conversions can be that if they're giving you trouble memorizing them. The thing is, the more practice problems you do, you sort of internalize those conversions as you do them. You're welcome. Okay, so the unit factors I need to keep in mind here. 1 kilometer. I always need to go through the base unit. I'm not going to remember exactly how many kilometers are in megameters, and tera, and peta, and micro, and nano, and pico. Trying to do the conversions just in my head or one step. I'm going to memorize, that there's 10 to the third or 1,000 meters in 1 kilometer, and in 1 megameter, 10 to the 6. Okay, mega. We have a lottery called the Mega Millions, right? So mega is a million. 10 to the 6. Okay, is 1 million. So that's sort of how I remember a mega million is 10 to the 6. Or a mega meter, I should say, is 10 to the 6 meters. All right, so those are my 2 unit conversions. This is just dimensional analysis like we've been doing literally all semester. And we're going to convert our kilometers to meters using this unit factor. Then I'm going to convert meters to megameters in the second step here. Beast, yeah, that's right. If your first M is capital M, right? Details matter. Okay, 1 millimeter is actually 10 to the negative 3 meters. Okay, so just be careful with capitalization because in science it matters. Units matter a lot, right? NASA has crashed satellites before because they were using like inches instead of centimeters or vice versa. Fun story. Hey, Laylo, welcome back. Yep. A lot of you have probably did this as millimeters instead. Okay, so just a good refresher that this capital M here is mega. Okay, so multiplying across the top, dividing by bottom, that means this should get a factor of 3 smaller, so 1.50 times 10 to the 5th. So the answer should have been, I think it was C. I think only 2 out of 8 of you selected. Feels bad, man. Definitely going to see some unit conversions on the final. And that's like what we did first week. And we've been sort of incorporating them all semester, but, a problem like this we haven't seen in a while, so definitely go back and refresh Exam 1 stuff, especially well, because you're going to have, 20% of the exam or something is going to be that material. And it's been a long time since we've used certain topics. It's alright, yeah, I mean, just make sure you're taking your time. You should have plenty of time on the final. It's super easy to go too fast, okay? And you can bet that one of the multiple choice question is on the exam, one of the possible answers is going to be mistaking mega for milli. All right, let's move on to the last one I have prepared, and then I'll get to some of those other practice problems you want covered. Again, at any time, paste in the chat any topic you want to see covered, any practice exam question, or any practice problem from the packet that you want to see covered, and I'll work through that explicitly. You have to tell me what concepts are giving you guys trouble so I can best cover those. Alright, so we'll leave this one up for a few minutes, give it a try, and I'll solve it in a few minutes. And I'll put up a poll in the meantime.
Open the world of music, a new streaming service with the official audio and video, playlists, live performances, and the rest of the story you can't find anywhere else. It's all here.
Correct, Brad. Ideal gas law, Charles law, Boyle's law, Lusak's law won't be on the final. Okay, so if you're having trouble remembering what Boyle's law or Charles law or Lusak's law or what the ideal gas law is, put them on your index card, or the mnemonic we learned in class about Beyonce's pyramid. Okay, maybe another minute to enter your answer. Looks like one in a landslide. We'll just close it there. I think one is correct, so good job. Feels good, man. So this should be PV equals nRT. Okay. How do I know that's the formula? Well, let's identify all the given information and what we're asked for here. We're given 1.06 moles of helium. So N is 1.06. That helium exerts a pressure P of 0.750 atm at 210 degrees Celsius, so T is 210 degrees C. What is the volume? V in liters. Okay, and I'm also told R 0.0821 liters atmosphere per mole Kelvin. Sorry, Beast, to let you down. There will not be any problems involving melconium, the as yet still undiscovered element. Right. Automatic A in the class if you discover and name an element after me. That will always hold for eternity. Okay, so here's the given information. So I need one equation that relates all these to the one unknown. So clearly that has to be PV equals nRT here. Pivnert. Right, the other gas laws we learned about were Boyle's, Charles, and Lusac. Right, I summarized that with this pyramid I call Beyonce's pyramid, because the mnemonic is Beyonce visited class today, learned plenty. If you weren't in class that day, you really missed out. When Beyonce visited class today, learned plenty. So Boyle's is P and V, that's what it's next to, so Boyle's law is P times V. P1 V1 equals P2 V2. Charles' law, V is over T, it's V1 over T1 equals V2 over T2. Lusac's law, it's next to pressure and temperature, so it's pressure over temperature. P1 over T1 equals P2 over T2. Okay, so that's how I remember the naming of those three different laws. For this one, though, it's Pivnert. PV equals nRT, so I have my 0.750 atmospheres times my X number of liters, that's my volume, equals my N moles, 1.06 moles, times R, which is the gas constant here I'm given. The single unit, liters atmospheres per mole Kelvin, right? All of that is with the number 0.0821. And then temperature. And we have to be careful here. This gas constant is in Kelvin, so this temperature better be in Kelvin, right? So we have to convert this 210, which all of you correctly did, to 483. Add 273. More correctly, there's decimals involved, but in this class we just add 273. 483 Kelvin should be the temperature here. Okay, so now this is my one equation. I have to divide both sides by 0.75. And just to make sure of units here, my atmospheres is going to cancel with atmospheres, my moles is going to cancel with moles, my Kelvin is going to cancel with Kelvin, and I should be left in liters, which is good, because that's what I'm solving for, volume in liters. All right, and I should get 56.0. Okay. Any questions on that one? Doc, don't start. You know there's never any extra credit in this class. Not allowed, but welcome. Lol. Shout out for Doc, biology, neuroscience, biochemistry sometimes. He merges into the chemical field. But great streamer, also part of the Knowledge Fellowship, in addition to Midnicorn and Innovata. Again, check them out. You streaming later today, Doc? Beast wants to know, is it possible to explain the origin of the ideal gas constant? Sure. It essentially is there to correct for units. Okay? It's the ratio of all these units to one another. It's basically all it is. It allows us to relate pressure and volume to moles and temperature. Okay, without getting, all these units jammed together. Because the unit of pressure you can't directly convert to a unit of temperature. That doesn't make any sense. So that's kind of what the gas constant does. Well, taking care of some housework, yeah, I understand how that goes. My morning was hanging up Christmas lights. It was a great way to start the day. Loved it. Probably hard to see, but I have a little chemistry over there. Chemistry. My Christmas tree and lights around. The lights aren't on right now, but you can be sure when it gets dark at 5, they will be on. Alright, so that's about an hour of the problems I had arranged to go through. The rest of the time is really devoted to what practice problems you want me to cover. I already had a couple ask for dilution problem and that isotope problem. So I'll solve those next. But again, if you have particular practice problems you want to see worked out, or topics, or just questions about the final in general, I'm here now. Ask them now. That is your best time to do so. Let me go back up here and see what exactly was asked. Dilution and isotopes. Brad seconds that notion. I'll do dilution 1. Let me just write down here George's question from earlier. Z has 2 natural isotopes. I'm a professional. Z has 2 isotopes, Z79. It's been a while since we talked about isotopes in class, so we'll go over those briefly. And Z81. Calculate the atomic mass. Of Z, if percent abundance Z81 equals 49.31%. Okay, and then we'll do a dilution problem. My penmanship is excellent. Uncle Bill, welcome. Sage says, Alex makes dilution seem so confusing. Yeah, sometimes that homework software overcomplicates things in order of calculating, just the moles. In a fundamental sense, it's the right way to do it, but it really overcomplicates it for our purposes. Welcome, Uncle Bill. We're doing an exam review for the final on Monday and Wednesday for my Introductory to Chemistry class. Okay, so things like molarity, the periodic table, isotopes, electron configurations, molecular geometry, all these things the students will be tested on in their final, so we're sort of reviewing those. Oh, is the mic a little low? Okay. Is that any better? Sometimes when I move far away, or I think I moved the mic. Is that any better, Lalo? Or still low? How about now? All right, thanks. Cool. All right, so let's do a dilution problem first, which I'm just going to pick here. Yeah, we started playing music about halfway through, so I was messing with the levels then. Alright, so this is, I'll just write out the problem, but it's one in your practice problem packet. A stock solution of nitric acid is 12.7 molar. If we dilute 25 mils of that solution to a volume of 0.5 liters, what is the concentration of the final solution? Okay, so take 2 minutes to try to solve this one. Maybe we'll do a poll for the answer. All right, so once you calculate your final answer, go ahead and enter in the chat 1 through 5, corresponding to what you think the answer is. You can either read in the chat for those options, or there should be an overlay in the lower left of the different options. Zaya wants to know, are there going to be any problems where you use molarity to find the solute mass or volume, like in Alex? Yep, that is definitely an option. I cannot confirm or deny whether those particular problems will be on the exam, of course, but definitely fair game to ask one of those. So yeah, I'll add one of those in just a second. This doesn't sound very Christmassy anymore. Indeed, it is not. I gotta go back and find more. There we go. Much better. Gas law equations are not provided. Right? So go write down or memorize Beyonce's pyramid and PV equals nRT. Mason, what date did you say you were going to go over isotopes? What day? We went over isotopes several weeks ago. I don't remember what chapter, but the problem right after this, I will go over isotopes. I wanted to get through this dilution problem since it was asked first. All right, we'll close the poll on that. Maybe I'll stop doing polls. 6 for 6. You guys are on top of it now. All right, so 0.635 was indeed the correct answer. 10 bonus points for everybody that voted. And got it right. So this is a dilution problem. Right, we talked about molarity earlier. We can either identify the problem type when it asks us a capital M or molarity. It's either going to be a direct molarity kind of problem, like we practice, or a dilution problem, which means we need a different formula. This is a dilution problem since we're told it's diluted. And the formula for that we're always going to use in these types of problems is M1V1 equals M2V2. Okay, so now just go through the problem and identify what is M1. Well, the first molarity is 12.7. What is V1? 25 milliliters. Okay, what is M2? Well, we're asked for that, so that's going to be what we're solving for. What is V2? 0.5 liters. All right, but be careful here because the units have to match up. Okay, so they can either both be liters or both be milliliters or both be nanoliters. It doesn't matter as long as those units are the same. Okay. So really you have to take this 0.5 liters and convert it to milliliters. Using our familiar 1,000 mils to 1 liter conversion. So this becomes 500 milliliters. And now we isolate for our unknown. If you keep track of units, the only unit left should be molarity. So 12.7 times 25 divided by 500. We should get 0.635. Any questions on that? If not, go on and try to solve this isotope problem, and then I'll go over the concept of isotopes and then walk through this problem. All right, let's cover isotopes and work out this problem. I put up a poll in the chat just to see what you guys' thoughts were for what percentage of my students actually completed the online instructor evaluation form. Limiting reactant? Sure, Brad. I'll stick around as long as there's lots of people still involved in asking questions. It would help, Brad, if you picked out a particular one. That would save me some time from having to look one up. All right, so isotopes are atoms that have extra neutrons, basically. So we went through earlier this notion of atomic notation, right, where we had an element symbol, its total protons plus neutrons, and its mass number, that is, and its atomic number or number of protons to the lower left. So that's atomic notation. There's an atomic notation that describes an atom of carbon like this, C13. That means there's one extra neutron. Okay, so Z79 and Z81 are two different isotopes of the same element. You guys weren't far off. It was about 40%. Thanks to those that did. Appreciate it. This problem in particular wants to know what the atomic mass of Z is, okay, given a certain percentage. So these atoms can have different numbers of neutrons in their nucleus, okay, but they're still that given element because they have the same number of protons, okay. And in nature, there's, carbon atoms with 6 neutrons and carbon atoms with 7 neutrons, okay. That corresponds to carbon-12 and carbon-13, and there's a certain percentage of each in nature. And this question's saying, in nature, there's these two isotopes of fictional element Z. One is 49.31%. What is the atomic mass? Okay, the atomic mass is always the average mass. If you were to, pick up a rock made of just element Z, okay, the average atom's mass in that whole rock would be a certain average mass. Just like for carbon on the periodic table, it says the average atomic mass is 12.01. Okay, it's not 12 because there's not just carbon-12. There's a little bit, about 1%, carbon-13, which is heavier. So that pulls up the mass from 12 to 12.01. Okay, so here we're trying to calculate that average atomic mass. And it's always going to be equal to the mass of that individual type of atom times its percentage in decimal form. So plus the other element's atomic mass times its percentage in a decimal form, so divided by 100. Okay, and you do that, you add them all up for all the different elements here. Here there's only two, or all the different isotopes, I should say. Here there's only two isotopes, so I only have these two. Okay, and I'm trying to figure out this atomic mass. Okay, the only complicated part here is I'm only given one of the percentages, so it's sort of implied what the other one is. You have to realize that if one's 49.31, the other one is 100 minus that number. Okay, so that's the only tricky thing here is, there's a calculation you have to do before the calculation to figure out the percentage of this Z79, and it's 50.69%. Divide by 100 to get it in decimal form, and now I have all the information I need to solve this. Okay, so I think that was George's question from earlier. Hopefully that helps you out, George. I get 79.903 is my atomic mass. Okay, which happens to be bromine. So mystery element Z here is bromine, right? Which you can confirm because that average atomic mass on the periodic table is 79.90. Yeah, you're welcome, George. What gives away that you have to use the combined gas law equation? Good question. Basically, you have to write down everything you're given, and you would be given sort of two pairs of pressure, volumes, and temperatures, and one would be left out. Okay, so it'd have to be phrased like the pressure of helium is 5 atmospheres in a 2-liter container at 298 Kelvin. Okay, if the pressure is changed to 10 atmospheres and the volume is changed to 1 liter, actually it's changed to 0.5 liters, what is the new temperature? So you would have to be given 5 data points and solve for the 6th. And in that case, you'd use PV over T equals PV over T. Okay, so hopefully that answers your question. Chai Mama. All right, so that covers dilution, isotope, limiting reactant we'll get to in a second. We were also asked, or somebody asked, about solving a different type of molarity problem, so I'll do that one now. Again, if you have other questions you want to see covered, you just have to type the topics in the chat, and I'll get to them. So this one's going to ask, what is the mass of zinc acetate dissolved in 200 milliliters of a 0.500 molarity solution? Okay, so again, I'll give you a minute to go through this, but I'll at least set up the equation. The plan of attack here is I immediately see a capital M for molarity, right? Which is also confusing because capital M could also mean mega if it's in front of another unit like G, megagrams. But if it's just a capital M, it means molarity. And as soon as I see that, I'm going to identify as a dilution problem. No, because it's not a change in volume or a dilution. So I'm going to write the formula for molarity. 0.5 moles molarity equals moles of that solute over liters of solution. Okay, and with that, I can see what other information I'm given in the problem, how to use this equation to proceed towards the ultimate goal of the mass or grams of zinc acetate. All right, so take a couple minutes, try to solve that. Paste an answer you get in the chat if you want, so that I know when you're done working, and then I'll cover that. Hopefully you guys like the fishy cam. With Lord Kelvin II. Looking splendid today as usual. Now he's going over to sleep, apparently. All right, so let's work through this molarity question. Okay, that I've sort of set up for you here. As for the mass in grams, now this looks a little intimidating the first time you read it because it's not immediately obvious how you're going to get to grams from a molarity. And that's why I always recommend writing this formula. Because now I see that I need liters of solution, and I have a volume. And I need moles of zinc acetate, which I don't have. So I can start with the liters of solution. Given 200 milliliters, I can get that into liters by dividing by 1,000. Which means I can use this molarity equation to essentially solve for the amount of moles of zinc acetate in this solution by multiplying both sides by 0.2. Thanks, Mason. Thanks for stopping by. Appreciate you hanging out. I'm here most Thursdays and Tuesdays. All right, so now we've calculated the moles of zinc acetate. I'm asked for the grams of zinc acetate, so this now you just need to realize boils down to a molar mass conversion here. And usually in these types of problems, I might give you the molar mass of zinc acetate. Okay, but here I don't, so you gotta add it up for yourselves. Consulting the periodic table, just don't forget about these subscripts out here. The 2 means, you know, I really have 4 carbon atoms and 6 hydrogen atoms and 4 oxygen atoms, but only 1 zinc, right? That 2 only distributes inside the parentheses. In any case, the molar mass I should get here is 183.49 grams per mole. So the final answer there should be 18.3 grams. Oh, that was terrible. So hopefully you were able to obtain that, or at least follow the correct procedure. Lord Kelvin looks like he's hiding. He's humble, afraid of the camera and all the attention it can bring. Karen, how did you get the 0.100 mole? Sure. That was this initial step here. When I started with writing down, I knew it was a molarity question, so I just wrote down the formula for molarity, which is moles over liters. And I filled in the given molarity, and I filled in the given liters. So I knew I could calculate moles from this one equation. Right? How do I isolate x, or question mark here? I multiply both sides of the equation by 0.2, and that'll then turn into this equation right below it. 0.500 molarity times 0.2 liters will give me the 0.100 moles. Right, because molarity really is moles per liter, so the liters cancel out and leave me that unit of moles. Okay, so hopefully that makes sense, Karen. Let me know if you're still confused. Up next, we'll do a limiting reactant problem, just for you, Brad. 4.1 grams of CR undergoes a combination reaction with 9.3 grams of chlorine gas. Yeah, this one's nice and difficult. I like it. Identify the limiting reactant and determine the mass of CrCl3 produced. So in all these, more challenging problems we've been doing later in the semester, in terms of reactions, we might have to write and balance the reaction. That's always the first step. Okay, so before we even try to get into the calculation, always try to balance the equation. Usually on an exam, I'll write the equation and you might still have to balance it or check if it's balanced, but sometimes you will have to come up with the reaction on your own. So this says it's a combination reaction, okay, which is the clue that two or more things are coming together to make a single product. Okay, here we have chromium Cr combining with chlorine gas. All right, this is a great problem because it really tests a lot of concepts. Combination reaction means these two things are coming together to make one product. Here I'm telling you that's CrCl3 that's produced. What's coming together? Chromium and chlorine gas. Chlorine gas, you have to remember, is one of the 7 special diatomics, so it's Cl2. And now we have to go through and balance it like so. Okay, so even just setting up the first part of the problem is, I'd say, just as challenging as the remainder of the problem. So now we have to identify the limiting reactant. Okay, for a limiting reactant problem, it's going to be 2 stoichiometry problems. So you're going to start with the 2 different reactants, chromium and chlorine gas. You're going to convert those into the grams of the same thing. Okay, here there's only one product, so that's what we're going to. We're always going to be calculating grams of a single product. Here that product is CrCl3. If there's multiple products, the question might ask you to calculate a certain product, or you just pick one of the 2 products and convert both to that same product so you can compare grams to grams of that same product. Okay, so stoichiometry dictates we need 3 unit factors here, right, to get us from grams of a reactant to grams of a product. So I'll start with the first one, 4.1 grams of chromium. The molar mass of chromium is 52 grams per 1 mole. And again, stoichiometry and limiting reactant, it's always molar mass, molar ratio, molar mass. Okay, so the middle one is a molar ratio. Moles of given on the bottom here in order to cancel, moles that I'm going to on the top here. And I consult the balance reaction. The whole point of writing and balancing the reaction is that for this middle unit factor here, there's 2 moles of chromium for every 2 moles of CrCl3. And the last one then is going to be the molar mass of CrCl3. Which I calculate to be 158.35 grams. And I'm going to set up the other equation similarly. Molar mass of chlorine gas is 70.9 grams per mole. The molar ratio is there's 3, because that's the coefficient in front of chlorine. There's 3 moles of Cl2 for every 2 moles of CrCl3. And the last unit factor is going to be the same. Okay, and both the top and bottom equations. Just to make sure my units are right, grams of chlorine cancel with grams of chlorine, moles of chlorine cancels with moles of chlorine, moles of CrCl3 cancels with moles of CrCl3, and I'm left with grams of CrCl3, which is good because that's what I'm asked for. Okay, so now it's just a matter of multiplying across all the top numerators, dividing by all the bottom. And making sure I'm not making some silly mistake here. Just to check my answer. Yeah, that looks right. So now I'm going to compare these two numbers and pick the lower one. Okay, I'm actually going to only be able to make 12.5, or more correctly 12 grams. That rounds down to 12 because there's 2 sig figs in the given information, so 2 sig figs means I can only make 12 grams of CrCl3, the lesser of these two numbers. And so chromium here is the substance that limits how much I can make. All right, hopefully that makes sense, Brad. Any questions on that one? That's definitely the most time-intensive problem you could get on the exam. Beast has another question, Incels has another question. I think we covered all of them, so we'll skip to those now. If you dissolve 16.2 grams of ClCl2 in 320 grams of water, what is the mass percent? Yeah, we haven't done a mass percent one yet. Mass percent, like all percentages, are mass of one thing over mass of total. So it's always 1 over total. So a mass percent is going to be the mass of the one item. So here it's 16.2 grams of ClCl2. Why do I know it's CaCl2? Because it says mass percent of CaCl2. If it said mass percent of water, I'd write water in the numerator. So it's mass percent of CaCl2. So it's just 16.2 grams of that CaCl2 divided by the total mass, which is that amount of grams plus the other items in the solution, which is water, times 100. So that's all there is to it here. It's 1 over total, 16.2 divided by 336.2 times 100. I get 4.82%. Yeah, you got it, Brad. No worries. So hopefully that helps, Beast. In cells, can you balance a double replacement chemical reaction? Sure. just find a practice problem to do. Let's balance the reaction of aqueous lead to nitrate with aqueous potassium iodide. A double replacement reaction to produce solid lead to iodide and aqueous potassium nitrate. Okay, and this will also test our ability to go from these written out chemical terminology to the symbols. All right, so we can practice each one of these. Lead to nitrate, that Roman numeral 2 means it's a 2+ charge. Lead, from I think it's Latin, plumbum is the name of lead in Latin, so Pb is the element symbol that comes for that. So the lead has a 2+ charge. Nitrate is a polyatomic. Okay, you have a table you can consult for that. That nitrate is NO3-. And so these charges essentially cross over to give us the ratio of leads to nitrates. It's 2:1, so that the charges are equivalent. Right, I need 2 of these single minuses to balance that 2+. Okay, so that's lead nitrate plus potassium iodide. Potassium is K. Iodide, that's for iodine, so that's I. Potassium is wanting to be +1 since it's in the first column of the periodic table. Iodine is a halogen, so it wants to be -1. That's a 1:1 ratio, so that just gives us Ki. I don't have to worry about any subscripts. And I should keep track of these phases. Okay, it's a double replacement, so I know the cations are switching places. So lead and potassium are the positive charged cations. They're switching places. So I'm going to make lead 2 iodide. Again, the 2 means it's 2+ for lead. Iodide still means it's I single minus. So again, we have to use the crossover rule to get PbI2, which is a solid. I also make potassium nitrate. Potassium still wants to be +1. It always wants to be +1. Nitrate is always NO3-. +1 and -1, that's a 1:1 ratio to give me KNO3. Aqueous. Okay, so that's a lot of the problem in setting up the equation. Balancing this one is actually pretty straightforward. And in these more complicated polyatomics, right, I'm wanting to treat this whole NO3, since it appears on the left and right as an NO3, I'm going to treat it as a single unit. So there's 2 on the left, 1 on the right. I'll clearly need a 2 out front and potassium nitrate to balance it. So that's imbalanced my potassiums, so I'll need a 2 over here. And that's convenient because now I have 2 iodines on the left and 2 on the right. So that's all there is for balancing this double replacement reaction. But that one does test you a lot in terms of taking these words and turning them into formulae. Okay, Incel, so hopefully that makes sense. You're welcome. Sure, Chamama. Volume of 12 molar hydrochloric that contains 3.646 grams of HCl solute. Lindsay, welcome. Can we review how to predict precipitation when 2 solutions combine? Yeah. So maybe I'll answer that one first before Chaibama. Just because we haven't really talked about it yet, whereas the molarity questions we've done a couple of. Okay, so how do you predict precipitation when two solutions combine? So even if this problem, we can treat this one here. Even if I didn't tell you what the products were, okay, the reaction might just say lead nitrate and potassium iodide combine in a double replacement reaction. Okay, double replacement is governed by solubility rules. Okay, so that's one keyword you have to keep in mind. Now, if you read double replacement, you might have to consider solubility. Otherwise, the question just might say what is soluble in water. Okay. So for double replacement, one of the products always has to be a solid. Okay, and this table of solubility rules describes, what will dissolve and be aqueous. Okay, that's called soluble, and what won't dissolve and become solid, that'll be solid instead, insoluble. So insoluble means solid, soluble means aqueous. Okay, so we use that table to predict what's going to be soluble, aqueous versus insoluble. So if this is double replacement, I know the lead and the potassium, the two cations, are changing places. So I know this is going to become lead iodide. Is that aqueous or is it solid? I come over here and consult the table, right, which I'll try to be able to read. Okay, so you'll see up here I can find I- in this one right here, halide ions, ClBr I-. So I- is usually aqueous, but keep reading the line. Exceptions are mercury, silver, and lead. So lead with iodine is an exception. Those are actually insoluble or solids. So that's how I know that this is going to be a solid here. Okay, potassium nitrate. Can I find potassium or nitrate in here? Nitrate ions are always soluble or always aqueous. That's why I know this is aqueous. Okay, so hopefully that helps, Lindsay. Just keep in mind that soluble means will dissolve, is aqueous, and insoluble, it's going to be a solid or a precipitate. I'll just write that here. Solid, precipitate, insoluble. AQ is aqueous or soluble or dissolves. You're welcome. Lord Kelvin II approves. All right, Chimama, can you do, what is the volume of 12 molar HCl that contains? Sure. Okay, so I'm going to read your question, try to identify what type of problem it is. It has a molarity in it, so I'm probably going to need the molarity formula, unless it's a dilution problem, which it is not. So I know it's going to be using the molarity formula, 12.00 molar hydrochloric acid. As soon as I write down that on my sheet, I'm just going to write the formula and leave some blank spaces. Molarity, this capital M, describes moles over liters. It's moles of that substance over liters of the entire solution. So now let's read the rest of the question. What volume, so ultimately I'm going to be solving eventually for this bottom number. What volume of this hydrochloric acid contains 3.646 grams HCl? And I'm also told the molar mass of HCl is 36.46 grams per mole. Okay. Is any of that useful? Well, in order to find the liters of solution here, I need to know the moles of HCl. And so this other information might be useful to obtain the moles, right? If I have the grams and I have the molar mass, I can calculate from that bit of information the moles of HCl. to then feed into this top equation, right? Hopefully that makes sense. You can start to see that. A lot of times it's about writing down the equation, and that'll sort of lay the roadmap for how to attack this problem. I can get from grams to mole by using this molar mass. Okay, given grams, G goes on the bottom so that it cancels. Remember that the number in a molar mass always stays with G. It always goes with grams, so it goes on the bottom here next to grams per 1 mole. Okay, so this looks like it's going to work out to be 0.100 moles of HCl. That's what I feed up here into this equation. So now I have 12 equals 0.1 divided by x, essentially. So now I just have to solve this algebraic equation. Okay, 12.0 equals 0.1 over x. How do I solve that? Well, I can multiply both sides by x. And I can get x. What you have to do is get x in the numerator by itself. So I've moved it to the numerator. Now I have to get rid of 12. So what I really have to solve is 0.1 divided by 12. So in this kind of setup, this 12 and this question mark or x are just changing places, right? So x is 0.1 over 12. So x, which stands for my liters of solution here, would be 0.0833, and that's always units of liters. You might be asked for it in milliliters, which means you have to multiply it by 1,000 to get 8.33 milliliters. Okay, so there can always be those metric conversions thrown in. Just depends what unit is asked for in the multiple choice or in the question.